So, assignment 4 is due on Friday the 26th. Exam 2 will cover chapters 4 and 5. So, this is chapter 4 we're covering. And then the final exam will cover chapters 6 and 7. There will not be a cumulative final, although the material from chapters 6 and 7 does incorporate pretty much everything from that came before it. Questions on assignment 4. Let me pull up a copy. Okay. Questions on this assignment?
Five A.
Yeah.
How would you like us to set that up?
5A. Just a picture of what the inverse image. I guess there should be a set of parentheses around this. We'll redo that. Yeah, it should be pre-image, left parentheses, and then 1, 2, 3, 4 right parentheses. And just although you can write it like that, what I wrote there, that would be okay.
So just like draw a graph of that.
It should be something familiar to you. Just draw a graph, yeah. Right, so in the standard XY plane, you know, the pre-image of these of this set here, you know, look at the pre-image of just one of those things, the pre-image of the set containing 1, you know, and then draw that, and then the pre-image of the set containing just 2, you know, goes, you know, is similar to it, and just draw the picture. It's a graph, sort of, or a collection of graphs.
Oh, I kind of see what we're doing there now.
Of course, we're just using integer points. We're not using all real numbers, right? So just points that are of the form a comma b, where a and b are integers, not just any real number. So essentially, you know, you'll draw the graph using all real numbers, and then just sort of blacken the integer points, make dots for the integer points. What else? What problems do you expect? Whenever you're trying to show a universal statement is false. So, you know, unless I said it, said or suggested it might be false, you know, it's going to be true. So in 1B, you need this counterexample. Show that A intersection B being empty does not necessarily imply that image A intersect image B is empty, by giving an example. So that's a counterexample to the universal statement. Now here in number 6, one of these statements is true, one of the statements is false. Okay, I guess I should say always there. It's always. It doesn't matter, you can take the word always out even. One of these statements is true and one of them is false. Okay, so you have to gonna have to decide which is the case. If it's true, prove it. If it's not, give a counterexample. Okay? You'll have to decide on that one. But all the other ones, no counterexamples in 5, because I'm only telling you what is the case. Oh, I'm sorry. 5C. Show that F is not surjective. It's not surjective, by giving an example of where it isn't, or not injective. Give an example of where it's not. Giving 2 elements. Let's write that down. So on 5B, actually let me write a little bit more down. So on 5A, so your answer on 5A will be, the collection, of integer points on some graph. So, for example, what I mean by that, like if you take the the graph y equals x squared, right, so here's like y equals x squared. The integer points are here. This is 0, 0, and then there's also 1, 1, and negative 1, 1. So hard to get this to draw nicely. Negative 1, 1. 2, 4. And negative 2, 4. So on and so forth. So your answer to 5A will be a graph with the integer points darkened in. Right? Every other point that I have showing here is not an integer point, right? Like, like 2 and square root of 2. Like here would be 2, and then the square root of 2 is here, but that's not an integer point. Then, so counterexamples. So, and on 5, on 5B, you want to show that this function here is not surjective, or not injective. So to show that f x y equal to x plus y is not injective, what do you have to do? All right, give 2 points, 2 domain points. What do the domain points look like? All right, this is a function f from z cross z to z. Oops. All right, so this is the domain. This is the range. So what's 2 points in the domain look like? X and Y?
Yeah.
I mean, I suppose it could, but that's not detailed enough. So the answer is yes.
As an ordered pair?
Yeah, the answer is yes, but not really. um, is that two elements of the domain? Is that two elements of the domain or just one? What's the definition of injective? So f from domain to range is injective when x not equal to y implies fx not equal to fy for all x and y in the domain. Now, of course, we're using x and y in half a dozen different ways here, but that's just simply par for the course sometimes for all you golfers out there.
So there's two domain points, so it's not injective.
Is this two things from the domain? This is the domain. Is that two elements of the domain?
It looks like it.
Elements, I guess. What is Z cross Z? It's the set of all. Set of all what? So, again, I was mentioning before, there are certain stumbling blocks, and conceptual stumbling blocks that people run up against sometimes, and one of them is Cartesian products. The other one is functions. Okay, so we need to think about what a Cartesian product is. So a Cartesian product, in this case, Z cross Z, is equal to what? It's the set of all
Ordered pairs of integers.
So what's an ordered pair of integer look like? What's an ordered pair?
What could be any pair of integers?
What are the characters that go into it? First character is left parentheses. Next character is
X.
X. Next character, comma, Y, such that X
Y.
and Y are elements of Z. Okay.
Oh,
How many things is this? It's one thing.
it's one. It's one thing because
It's
it's an ordered pair.
It is an ordered pair. It is one thing or one element of the domain. Okay, so now here's the definition of injective. So f from D to R is injective when x not equal to y. So this x and this y different from this x and this y. I'm talking about the same thing here. What are the x and y here? What are x and y here in this definition? They're elements of the domain. How many elements? How many elements of the domain here are there? What do I know about D? I know nothing about D. So when I refer to an element of D, I just call it X. I mean, if maybe that's getting to be.
There are two elements of the domain.
There are two elements of the domain. That's two elements of the domain. F from D to R is injective. So why don't we do it this way? Okay. So all right. So this is the abstract definition of a function being injective. What is the definition? So for F from domain Z cross Z to Z, F is injective when two elements of the domain. Give me two elements of the domain. Give me two elements of the domain. Name them. Give me two elements of the domain. Give me their names. I mean, not names as in, Mark and Sally. Names as in what elements of the domain look like. What do elements of this thing look like? We've been talking about it here.
X and Y or A and B.
I want two elements of the domain. Two. This is one element of the domain, like that. Two domain elements.
A and B.
A and B are not what elements of this set look like. Elements of this set look like that.
Are you looking for like actual numbers?
Nope. I want two elements of that set. One element of this set looks like that. I want two now. There's one element right there. A comma B.
Mm-hmm.
Give me another one. The rest of you guys sleeping, or?
B comma A.
That's too specific.
Negative A, negative B.
Still too specific. Have to not have anything to do with each other. Like, I mean, if A, B is one element, right, another element would be
XY.
sure. X, Y, P, Q, S, T, alpha, beta, whatever. Right? So, this is the abstract definition of injective. So I don't know anything about this domain here, D. All right, so when I want to refer to an element of D, I just call it X, or just call it little d, just call it Y, whatever it might be. Just refer to it as one symbol. This set I know about. It's a set I know something about. Its elements don't look like just X. Its elements are pairs of integers, ordered pairs of integers. Parentheses A comma B, and parentheses X comma Y. Right? So for F from Z cross Z to Z, right, F is injective when these two things being unequal implies that F of AB is not equal to F of XY. Of course, there's a gazillion examples of pairs AB and XY that are unequal, where if you add them together, they are equal, right? 0 and 1, add to 1. So to 1 and negative 1, add to 1. When are two pairs unequal, by the way? Is A comma B not equal to X comma Y? This is just a side note. And what does it mean for two pairs to be unequal? Does that mean A is not equal to X and B is not equal to Y? It's A is not equal to X or B is not equal to Y, right? I mean, like 1, 5 is different than 1, 3. They're different pairs. Doesn't mean that the first coordinate can't be the same or the second coordinate can't be the same. One coordinate or the other is different. And so, of course, so for all A, B, comma, X, Y, and Z cross Z. Right, so the definition of injective, abstractly, when applied to this specific function, looks like this. For every two elements, A, B, comma, X, Y, of Z cross Z, when A, B is not equal to X, Y, it implies that F of A, B is not equal to F of X, Y. Of course, this isn't true for all A, B, X, Y, and Z cross Z. You give give an example where A, B is not equal to X, Y, and F, A, B is equal to F, X, Y, to show the function is not injective. Now, here's an example like that. Example. So consider a function, let's call it G, from Z cross Z to the natural numbers defined by G of little a, little b, little a comma b, equal to a times b. This is not injective. Why? Well, give me a pair, two actual pairs now. I mean, not abstract pairs, two actual pairs, like, 3 comma 5. Give me two pairs that are not equal, but when you apply G to those pairs, it is equal. Actually, let's do it like this, since we're, well, no, actually, I can't do that, because gotta leave out the 0. Give me two pairs that are unequal, but when I apply G to it, it is equal. guys? Hello.
6, 1 and 2, 3.
Yeah, so 6, 1 and 2, 3. They're not equal. And f of 6, 1 is equal to 6, which is equal to f of 2, 3. Okay? So those two pairs are unequal, but, you know, when you apply, or not, sorry, not f, g, when you apply g to it, the pair, the function g, they are equal. They're both equal to 6. Right, or, I mean, there's a gazillion other examples. It's not just that. Also, like 0, 5 is not equal to 0, 0, right? And g of 0, 5 is equal to what?
Zero.
0, which is the same as g of 0, 0.
110 and 25 are not
110, 25, so on and so
They're
forth.
a lot.
Yeah. Basically, any non-prime number that you pick can be factored in a couple different ways. Or, no, sorry, not any non-prime. Any number that's not a prime or a product of 2, like 15. 15 you can, well, no, actually, because we're not insisting on primes. Any non-prime number you can factor in 2 different ways. In this sense that we're talking about. Normally you don't consider 6 and 1 a factorization of 6. Alright, so the previous example is just with addition. Alright, let's go back to our discussion. So, you know, I mean, I'm trying to pull answers out of you guys. You know, I mean, I need, you know, there to be a back and forth. I know sometimes you kind of feel like, well, I don't want to answer because I don't know what I'm saying. I might say something wrong and it's embarrassing or whatever. You know, yeah, I know that's true, but
Being put on the spot.
yeah, but it's very anonymous here. I mean, I don't know. I can't see you. You can't see each other. But also, I mean, it's a closed door environment, right? So, I mean, this is an environment where we're learning. So we shouldn't be afraid to say something wrong. You know? I mean, I know that's just idealism on my part. It's sometimes, you know, hard to avoid that. But no judgments here. You know, the only judgment that's going to be made is when I grade your papers, and that's it. Okay? Speak. If you say something wrong, so what? Right? You know, at least we get some conversation going. All right. So we were talking about. So that's enough talk about injective. Let's go back to surjective. So a function f from d to r is surjective, and then the more colloquial term is onto. Right. So with injective, the more colloquial term is 1-to-1. Although 1-to-1 is a very descriptive term, and it's a nice one. Onto is kind of awkward because it's not really an adjective. When the image of the function is r itself. In other words, for every y in the range, there is x in the domain such that y equals f of x. So, like, this function is surjective. Every range element has at least one arrow coming into it. Right? Here, this function is not surjective because I got range elements with no arrows going into them. Okay? In calculus, you know, all functions are surjective. Essentially, the range is not allowed to have things like this. But in a more abstract sense, in a more general sense, you can have that because, you know, the image of the function is not necessarily always apparent. All right, so consider f from R to R, given by fx equal to x squared. Is f surjective? And the answer is no. Okay, if you -1 is a real number, right, and -1 is not equal to x squared for any real number x. So there is a y in the domain such that every x in the range doesn't go to that range function. Sorry. There is an x in the range. There's a y in the range such that for every x in the domain, x does not go to that range element. But we can do it this way. The image of f, where f is equal to f of x is equal to x squared, the image of that function is just all the non-negative real numbers. So now if you consider the function f from R to the interval from 0 to plus infinity, all non-negative real numbers defined by fx equal to x squared, now it's surjective. Okay, here's the proof. Take y in the range. Y in the range, so y is a positive, non-negative real number. Well, what domain element x goes to that y? Now, when you specify that domain element that goes to y, your answer is in terms of y. So x will be written in terms of y. So in this case, we'll let x be the square root of y, and then f of x is the square root of y squared, which is y. Okay, so the answer is always in terms of y. So here's something slightly more a little more interesting algebraically. So here's a function fx, an algebraically defined function. Fx equal to 3x minus 2 over x minus 1. So such a function is actually called a Moebius function. Did anybody take complex variables yet? 3200. Anybody take that?
Not yet.
Not yet. That's a very nice class.
In the fall.
Yeah, it's a real nice class. It's not a proof-based class. It's another sort. I don't know. It depends who teaches it, I guess. Maybe a little bit as far as proofs go, but it's calculus using the complex numbers or imaginary numbers. And these types of functions have very, very interesting properties. Anyway, so it's called a Moebius function. Right after the famous Moebius guy named Augustine Moebius. I think it was Augustine. I forget. So that defines a function from the real numbers, except for 1. Of course, I mean, you can't let x equal to 1 here because you can't divide by 0. To the real numbers minus 3. So actually, you don't include 3 in the range. Why? Because, I mean, this function actually, I mean, if you graph this thing, what is it? I mean, it's got a horizontal asymptote at 3 and a vertical asymptote at 1. And the graph of this thing looks like this. Or, no, sorry. Like that. Right. But I mean, we're not really looking at things in that sense, in this more analytic geometry, calculus type sense. We're just trying to get these definitions straight. All right, so that defines a function from here to here. Is it surjective? So show that f is surjective. So that is, for any y in the range is r minus 3, there is x in the domain such that y is equal to f of x. Okay, now the answer you give should be in the answer you give for x should be in terms of y. of y, when talking about algebraically defined functions. Elementary functions from calculus. Elementary functions are polynomials, sines and cosines and exponentials. Right, all the functions you're used to: sine, cosine, logs, exponentials, polynomials, rational functions. All those functions that you've been encountering in the standard calculus classes. Those are called elementary functions. There's actually you can expand the notion of elementary functions a little bit beyond that: hyperbolic sine, hyperbolic cosine. So the Airy function. There's also this thing called the Airy function. So the answer you give should be in terms of y. Now, how do you find it? How would you find it? This is actually an exercise you would have done in your pre-calculus type classes. All right, you just let y equal that expression there and solve for y. Right, so y times x minus 1 is equal to 3x minus 2. So we got xy minus y is equal to 3x minus 2. Move all the x terms to one side and all the non-x terms to the other side. So I have 2 minus y is equal to 3x minus xy. Factor out the x. Right, so we have 2 minus y over 3 minus y is equal to x, which is an element of the range, right, because y is not equal to 3. Right, I mean, you would get into trouble here if y was equal to 3, but the range didn't include the 3. That function has a horizontal asymptote at 3. Right, so in this case, f of 2 minus y over 3 minus y is equal to y. Shall we check it? You can check it if you want. What was that function? All right, f of 2 minus y over 3 minus y. What was that function f? The function f was 3x minus 2 over x minus 1. So 3 times this thing I think that's it. Yeah, 3x minus 2 over x minus 1. So now you actually have to, do this calculation. So this is 3 times 2 minus y over 3 minus y times 2 times 3 minus y over 2 minus y minus 3 minus y over 3 minus y. So these cancel, and you get 6 minus 6 minus 3y plus 2y. So it's minus y. And then on the bottom here you have so it's 2 minus 3. And then minus y plus y, so that's minus 1. That's y. Okay? So that's a little more entertaining algebraically to solve that function there. All right. So that's everything you need for this assignment. Surjective, injective functions 4 and 5, or 5 and 6. I mean. Okay, so please, let's get this going, and let's answer questions on Monday, and then you can finish it up and hand it in on Friday. All right. All right. So a little bit more to talk about in this section, although this doesn't pertain to the homework, directly. So statements saying the following are equivalent. So this is something you'll see in mathematics a lot. The following are equivalent. So when somebody says the following are equivalent, one, and then here's A. 2, here's B. 3, here's C. 4, so on and so forth. Blah, 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 blah. So when someone states the following are equivalent, it means that A if and only if B, and B if and only if C, and, well, let's put a fourth one in there, D. So A if and only if C, and A if and only if D, and B if and only if C, and B if and only if D, and C if and only if D, blah, 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 etc., are all true. In other words, either all of A, B, C, and D are true, or all of A, B, C, and D are false. A, B, C, D are true, or all of A, B, C, D are false. They're logically equivalent in a pairwise fashion, right? So how many proofs are there? I mean, to show So recall that A if and only if B was logically equivalent to A implies B and B implies C or A. Right. So to prove an if and only if statement, right? You need to prove two implications. Oops. To prove two implications. So here, if you're saying the following are equivalent, A, B, C, D, E. And that means A if and only if B is true, A if and only if C is true, A if and only if D is true, B if and only if C, B if and only if D, C if and only if D, blah, blah, blah. And each one of those is two implication statements. So like here, I mean, if there's only 4 things, that means you got to prove 8 implication statements. Right? You'd have to prove 8 implication statements. I mean, that's a lot. But you don't actually have to prove all 8. Okay. You would need to prove. So, however, well, okay, so let me say what I just said. So, to show, 4 statements, A, B, C, D, are all equivalent, you would need to prove oh no, I'm sorry, it's 12. 12 implication statements. Well, 6 if and only if. Which is 12 implications. So in actuality, however, it's much less than this. So the hypothetical syllogism tautology, however, cuts down to 4 at the least. At the very most, sorry. Cuts this at best. All right, by proving the following implication statement. So a hypothetical syllogism is this, is like whenever A implies B and B implies C, that's it implies, not logically equivalent to. A implies B and B implies C implies A implies C. So whenever you have 2 implication statements like this going through B, it gives you the third. And so if you have A implies B and you have B implies C, then this is automatically true. So in order to show A if and only if B, B if and only if C, C if and only if D, D if and only if A if and only if C, and B if and only if D, it would suffice to show that A implies B, B implies C, do it this way, B implies C, C implies D, D implies A. Or, A implies C, C implies B, A implies C, C implies B, B implies D, or D implies A. Or, anything similar to that. You could also have like this, A implies C, C implies B, B implies A, and then B if and only if D, etc., etc. I mean, there's different schemes. As long as your scheme gives you implications in both directions for each pair, you're fine, right? Here, A implies B and B implies C, therefore A implies C, right? A implies B, B implies C, therefore A implies C. Right? And then C implies D and D implies A, therefore by hypothetical syllogism, C implies A. So I've got A implies C and C implies A. So we're good to go there. right? Also, I have A implies B. Here's A implies B. How do I get B implies A? Well, B implies C, and C implies D, and D implies A. Therefore, B implies D. Or here, right, I have A implies C, A implies C, and then C implies B, which implies A. So that gives me C implies A. Or I have A implies C implies B implies D. So A implies D. And then D implies B, and B implies A. Therefore, D implies A. So it gives me arrows in both directions. So as long as you have this sort of connected arrow diagram, right, that's all the proof you need, because hypothetical syllogism does all the rest for you. Hypothetical syllogism does the rest for you. So the example, which we'll prove next time, is as follows. Let D and R be finite sets. So finite sets, not infinite. The following are equivalent. Or let be finite sets, and F be a function. Sorry. Consider, let me say it this way. So consider a function F from domain to range where D and R are finite sets. So no infinite sets here. The following are equivalent. One, F is a bijection. I didn't define bijection. A bijection is something that's injective and surjective. So I guess let me give a definition there. F from domain to range is a bijection when it is both injective and surjective. Both injective and surjective. So that's a bijective. So bijection or bijective or whatever, right? Bi meaning two in this case. So consider a function f from D to R, where D and R are finite sets. The following are equivalent. F is a bijection, F is an injection, F is a surjection. Or F is bijective, F is injective, F is surjective. So injective and surjective gives you bijective, but with finite sets you only need one of them. Once you get injective, then you get surjective automatically. Once you have surjective, you get injective automatically, and therefore bijective automatically. So we'll prove this. 1 implies 2, 2 implies 3, 3 implies 1. Okay? But next time. Okay, guys, have a good weekend.